absolute pleasure to present Professor Leman Akoglu. She is the Heinz Colleagues Dean Associate Professor of Information Systems at Carnegie Mellon University. And her research focuses machine learning, data mining, graph mining, pattern discovery, and anomaly detection. It's super difficult to work in this area and never have run into one of her papers. And at Heinz, Dr. Akoglu directs the Data Analytics Techniques, Algorithms, and Data Lab. She's the recipient of the SDM-IBM Early Career Data Mining Research Award in 2020, and NSF Career Award in 2015, a US Army Research Office Joint Investigation Award, has patents, and has been funded pretty much by every company under the sun. So we have someone I believe to be a true rock star here. I'm super happy that we have her. Thank you so much, Leman, and please, the floor is yours.
All right, thank you very much, Christian. Good afternoon, everyone. A very pleasure to meet you. I'm very excited. I like graphs. I love graphs, and I see that I'm in between like-minded people. So I thank very much, Christian, for inviting me, and Pierre for organizing everything nicely. So let's talk about anomaly detection. I call it for finance because I got the fortune of collaborating with Capital One Bank in the US as well as PwC on financial problems using graph algorithms and other tools that I'll share today with you. Obviously, we know that anomalies are these interesting observations that stand out as different, that are usually pointers of faults or inefficiencies in systems, in many systems. So today's focus is going to be obviously financial domain. And in my talk, I have two parts. So in the first part, I will actually illegally chose a route of not talking about graphs for a bit. We'll talk about tabular data and outlier detection, where the data is distributed in multiple machines. And in the second part, I will shift focus to relational anomaly detection with a specific accounting fraud detection application. All right? So let's get started. So the question here is, financial data is often cloud resident, so the data is collected in a distributed manner, maybe across continents in different servers. If you were to find outlier tabular points in feature spaces, how do we do that with distributed algorithms? In an exact way. So we don't want to resort to subsampling or local model averaging, none of that. Exact outlier detection in a distributed manner. So when we faced this problem with Capital One, we didn't have any open source tools to solve the problem of outlier detection for distributed data for large and large D scenarios. Remember, tabular data is this N by D matrix, right? And points, N is very big, usually billions of points, and then D can also be very big, like millions. And so for large and large D, there was nothing out there that was open source. So we designed a Sparks algorithm. As you can guess, it is an Apache Spark-based open source implementation of outlier detection algorithm that we designed, that I will introduce. And of course, for small and small D, there are many algorithms, right? Single machine algorithms. And for, there were other academic or open source algorithms for large N and small d and small n and large d that I will compare in the experiments that don't scale for either N or D and vice versa, okay? Of course, Amazon has their SageMaker and right, all other kind of internal distributed streaming outlier detection algorithms, but they're not open source for the community, so we wanted to design that solution. What are key points of Sparks? So it is distributed under data parallel detection. It scales linearly in both time and space, and it handles both large N and large D, scalable to either scenario. It can handle mixed type attributes, categorical or numerical, which is a typical setting for finance. It's robust to hyperparameter settings. Remember, outlier detection is unsupervised, so you don't have labeled data for model selection. So it has, you need either robustness or some unsupervised model selection. And being an ensemble approach, this is quite robust to hyperparameters. And finally, but not the least, open source solution. So back in 2018, we had designed a single machine version of this algorithm called Extreme. And so here we scale to a large number of points, large feature spaces, possibly evolving. And that's what I want to draw your attention to. What does that mean? So typical streaming scenario on the left assumes that new points are coming over time, right? So D is fixed, you fix your feature space, and sort of new points are coming one at a time, right, over time. So this is time, right? Time is the vertical axis. And new points are coming over time. Color is for a different point. Maybe it's a customer ID, right? Think about it that way. So in the new setting on the right, we have not only new points are coming over time, right? Purple over there, and then blue comes in, right? New customers are coming in. But also new features may also arrive over time. So the feature space may evolve. Why? Because maybe you decided to add new features, or maybe you were tracking, say, number of unique websites that a person visits, right? How many times a unique website was visiting? Well, guess what? New domains are always coming in, right? New features are also coming. And thirdly, existing customers may change feature values, right? So this guy, purple guy, right, later on changed their value by delta amount. Over time, the values may also change. So it's not like frozen values. So how can we handle this type of outlier detection in this kind of data? We call it streaming evolving, feature evolving. So we handled it in 2018, and this is the paper that I am referring to for single machine. And now in 2022, we scaled it for distributed data, designing the Sparks algorithm, taking extreme, making it on Apache Spark. And the algorithm itself has 3 stages, so 3 components that I will outline, maybe a little deep dive into the technical details next. All right. So first stage is projection. So think about it as data sketching, like representation learning. You may say, why do I need representation learning? It's already tabular data, right? It's already structured. Well, we need to learn sketches. We need to reduce it into lower dimensions because, right, high dimensions, we want to learn the manifold. So how do you do that typically? How do you sketch high dimensional data? You might have heard about random projections, right? There may be a lot of mathematicians among us. So you take these random vectors, as many as k, if you want to reduce a k-dimensional representation. In this example, we have 3 such vectors, and you just randomly project your vector data x by dot producting, so you get a 3-dimensional embedding, right? Random projections. So these random vectors could also be binary random, right? Theory says that for sparsity purposes, they're easy to store that way. So you can have -1, 1, or 0 entries in these, very sparse. And it will do the job of preserving pairwise distances, so it's all good. The problem is these random vectors need a fixed dimensional size, right? You need to pre-specify them, but in our case, the feature space is unknown. It may be evolving, remember what I said. So what do we do? Well, the answer is don't cache, hash. What does that say? Don't pre-specify these vectors and cache, right? You don't need to pre-specify them because you don't know D. What you'll do is you're gonna specify instead of k random vectors, d-dimensional vectors, you'll specify k hash functions, h1 through hk, and every time you see a feature, you will just hash the name. So for example, it's a categorical feature, color red. You're just gonna pass that color red string into this hash, and it will spit out a value from the set +1, 0, and -1 with some probabilities. If you want more sparse, 0 has higher probability, etc. Right, so you're basically taking a feature name, a column, let's say here, and then the hash function generates a 0, maybe -1 for this, 0 for this, +1 for this. Like on the fly, you can compute those values. You don't need to cache them. And now new features may arrive all they want. All I need is the name of the feature, and then I just pass it to the k hash functions. Each one of them spits out the values, right? So imagine f+1 arrived here. My hash functions h1 will spit out maybe 0, h2 +1, right? I know the entries on the fly. So it can handle streaming stuff. How do we do that in Apache Spark? So if some of you are familiar with MapReduce paradigm of working with MapReduce implementations, key value pairs. So projection, the sketching that I just described is very easy to do. You just need a map face. You don't even need a reduce because all you need to do is pass these k hash functions to the worker machines. Each one of them holds a part of the data points, right, x's, and they'll just pass each point through these hash functions, and the k-dimensional representations will reside in their local storage. So fully local, no reduce, no network communication. Okay, now we have our sketches, right? We reduced into this low-dimensional manifold. How do we do detection? We're going to do if you're familiar with the isolation forest algorithm for outlier detection, which is this extremely randomized trees, right? It does these randomized cuts in the feature space. And we do a version of it where, imagine you have this two-dimensional space, right? So two features, x1 and x2. It ran extremely randomized. It first randomly picks a feature and cuts the space at a random threshold. Instead, we'll do half space cuts. So we'll find a min and max and cut in the half in between. Maybe the first level I picked x1, so I cut the space in half. Then I picked maybe x2 as the second level at random. I'll cut another half. So now I have 4 quarters. In the third layer, maybe I will pick x1 again, so I cut the existing halfies into more halfies. Now I have 8, right, et cetera, et cetera. So I keep cutting the space into these little hypercubes, if you will, right? And I'll just do counting. Why? Because we like counting, right? We're like statisticians. So I'll just count how many points fall into what? Bin. The way we do that is computing what bin index each point corresponds to. So if I have this point 2.2, 3, right? Two-dimensional point y over there. In the first cut, it falls into the first bin, no bin for the second one. In the second cut, it also falls into the first bin, so 1, 1, index of the bin it has. Later on, when I cut an x1 again, now it's in the 0, 1, second bin on x1 and first bin on x2, right? So you can compute these bin indices on the fly. And then all you need to do is you need a counting data structure. So all the points in the same bin or hypercube will have the same bin ID vector, this Z bar, and then you just need a counting data structure like a count min hash to accumulate the counts. And okay, having looked at how this works, how do I do this with MapReduce? Very simple. First, we're gonna specify the cut points, like what features I'm cutting at every level of a chain. We call this half space chain. Like chain because every level you're cutting more and more, so it's getting deeper and deeper. So every level I need to decide what feature I'm cutting on, and this is random. You just randomly draw things. But all the worker machines, right, all machines in the distributed setting should share the same cut points. All cuts should be the same. So that is being shared across workers. And then the workers or mappers will output key value pairs of the form. For every point that they have, they will compute the bin vector ID, Z bar. This is the key, comma, 1. So I've seen 1 of those, right? And then you do reduce by key, meaning all the points with the same key. What is the key? The bin index, right? Will be aggregated with the sum. So reduce will be the sum function, basically finding the total count for every unique bin that you have. So this is just histogram counting. Right, very simple, only one MapReduce phase, right? It's not iterative. Second phase is done. Now, how do I do anomaly scoring? Well, I have an ensemble of half space chains, so I have actually created M of them, let's say. So having done the counting, H here stands for the count min hashes that I have. They are doing approximate counting. What we need to do is, again, pass those information, the accumulated counts after the reduce by key phase, back to the workers, right? And the mappers will simply compute anomaly score by saying, given a point y, okay, let me first compute its Z bar, the bin index, at every chain, at every level, and then extrapolate the count by 2 to the L. Remember, I'm doing half space chain, so I need to extrapolate. If you're at level 1, if everything was uniform, how many in total would you have? At level 3, there are 8 bins, right? So 2 to the 3 times 8 points, if things were uniform, would be the, so I'm kind of like putting them onto the same scale because, right, over different L's, I'm gonna sum these scores. And if a point lives in a very sparse bin with very few total count, then its anomaly score will be lower. So the lower, the more anomalous. It's really just histogram counting. So then how do I do this on Spark? One map phase, because now all I need to do is pass these chain informations to the workers, and each worker can do this calculation for every X or Z that they have, for the point that they have locally, and store the outlier score. And then all I need maybe an overall ranking at the end. Okay? So that's it for Sparks. We evaluated on 3 large public data sets along with capital 1 data for fraud detection that I'm not allowed to talk about. but the public data sets are 3. So specifically 3 types. So we have GSET, which is this mid-scale and mid-scale D, 5,000 features. OSM is a bike GPS trajectory data set, so people report 2-dimensional is GPS data, but 2.7 billion trips, so bike trips. And this counts as large N but tiny D data set. And then we have spam URL, where we have a million of N and millions of D, and notice D is larger than N even, so right? We're going to compare our Sparks to 2 open source other distributed outlier detection algorithms. SPIF is the Spark version of isolation forest. It's model parallel. It's not data parallel, so it doesn't really scale with data very well. And dbScout is data parallel. It's the outlier detection version of dbScan, if you're familiar with dbScan as a database algorithm. Okay, so how do we do? So let's first look at GSET, small and large D problem. Here, what happens is dbScout just fails, because dbScout only scales up to like 10 dimensions, you see. After 10 dimensions, it's just timeout. It just the time grows exponentially fast, so it just dies. So we only can, and this is only 10, right? Versus the data is 5,000 dimensions. So then we just compare to SPIF, and we do better in terms of detection performance, AUROC, than SPIF, across different hyperparameters. So remember, hyperparameter configuration is very key for outlier detection. We don't know how to set the hyperparameters. So the fair thing to compare is you just run different hyperparameters and average the result. That would be corresponding to the expected value, expected performance if you were to pick at random the hyperparameters, right? Because otherwise you don't know how to do. You don't know how to set hyperparameters. So on average, we also see stable results, which means it's robust to hyperparameters. And then over here, you're seeing in blue SPIF across different hyperparameters, and in red are Sparks with different hyperparameter configurations, AUROC versus running time. So our AUROC is a bit better with a little bit more running time than SPIF, and then memory usage is also a little bit bigger than SPIF. All right. How about OSM? So this is billion N, tiny d. So here, SPIF is model parallel, so it actually cannot use all of the data. We use a very, very tiny fraction of the data for training these trees. And time, sort of, it gives memory error, timeout, immediately crashes after some amount of data. And then dbScout works well here because D is very small. But if you look at the F1 performance versus running time, dbScout here is in green. Different symbols correspond to different hyperparameters, so it's very sensitive to hyperparameter, you see, because it's nearest neighbor based, and number of nearest neighbors is extremely crucial. You don't know how to set. So for different values of k, it's just all over the performance, all over the place. And SPIF is not doing very well here because it's unable to train on a lot of data, and then Sparks is striking a balance. Okay, let's move on. Last one, large and large D. Here, dbScout, we weren't able to run. Well, one thing you may say is, I know dimensional reduction, so why don't you do random projections or whatever you told me earlier? So let's do random projection for dbScout, reduce the dimension to 2 or 7. Again, more than 10, it explodes. So here you see with only 2 dimensions, again, it's very sensitive to hyperparameters, oscillating performance, and so on. So not doing very well. And then Spark and SPIF is comparable here, but remember, SPIF doesn't scale with N. So this is mid-N, but large D data sets. Okay. Okay, and one more thing, Spark offers 4 to 20 times speed up. So with number of partitions, this is Spark's partitions, right? Number of data partitions, increasing, the running time drops. Compared to a single machine running time, here this is the number for single machine, the savings are 4 to 20-fold. And scalability is in red here. Things scale up, but after a number of partitions, you spread too thin. Right now, network communication over-dominates, so scale doesn't go linearly up. You don't want to spread too thin. Things are linear in terms of data set size and all of that. So in summary, Sparks is this scalable distributed outlier detection algorithm, data parallel, linear time space, can handle large and large D, mixed type attributes, robust to hyperparameter settings because it's an ensemble, and more importantly, open source, so it's for everyone to use. One thing that I didn't mention is the original extreme algorithm was amenable for streaming because of the on-the-fly hashing and sketching and all of that. But we didn't implement Spark streaming. So Sparks is only static distributed because we ran out of time, but it's very amenable to take and also Spark streaming implement for streaming settings. This is the tiny URL for you to access the open source code if you're interested in large-scale outlier detection. And after working with Capital One, the Army approached to me and they said, we need to detect outliers, and also their data is already in AWS. So you can't tell them that, oh, pull all the data somewhere on my single machine and I'll run it no matter how big of a RAM machine I have. They're like, no, the data is already on AWS. Now what do we do? Right? So distributed detection. Okay. Maybe it's a good place to pause for a minute and see if you have any questions before we shift gears. Maybe at the end. Okay, so we'll do that. If you have any questions or clarification questions at any point, just raise your hand. I may be going too fast. Okay, so the next one now is about graphs. We are shifting gears here a little bit, different problem. So what's the problem? Informally, the problem is, here are millions of journal entries. How many of you know what a journal entry is? Okay, one person from accounting. Okay, I didn't know what it was. So I guess most of you are not from accounting, so I'll explain what that is. I had to educate myself, learn a lot about accounting. But then we'll see that a journal entry can be thought of as a graph, which is what we like to see. And then we'll find anomalies, right? Entry errors, maybe human error or misconduct, any shenanigans in the accounting and things like that is the informal problem. But really, a journal entry is nothing but a graph. Why so? So in accounting, there is this thing called double entry bookkeeping. So they will report every purchased item as it's like an itemized receipt, think about it, right? You go to a restaurant, you buy 10 things, every one of them is itemized. And so when a company makes a purchase, like they buy 10 printers, they will itemize every one of the printers, or they buy trucks, or they pay something. Everything is itemized. The simplest journal entry is two entry, okay? So money comes out of gross sales. It's a credit of the amount, negative. Where does it go? Well, it goes to accounts receivable, debited, that same amount. So all the numbers sum to zero, right? Every number is recorded twice as credit and debit, because from one account you draw from credit and to debit. Okay, that's my best effort explanation of what a journal entry is. You take this, well, all you need to do is now which account it came from, which account it went to, two separate nodes as accounts, and then transaction as the edge, and you can put that dollar amount on the edge, right? So it's a graph. Simplest journal entry is a two-noded, directed-edged graph. Okay, it gets more complicated. Some of them has more lines, right? So maybe we got gross sales, sales tax also on top of that. Maybe we bought two things, two things, and then total tax, and we will debit it to the receivables. Okay, so this is a four-node graph. Four unique accounts are involved. Directed, right? Because I draw from one account and put in another account, directed edges. The amount is the edges are weighted, and nodes are labeled by the account type. So there are different ways to label the nodes in accounting. I work with an accounting professor at Tepper School of Business. And simplest, you can call them revenue, liabilities, assets, 3 labels, or 3 or 4, but you can go more granular, like sales, receivable, right? Different labels you can give. So it's a node labeled, directed, weighted graph. Here's an example of transaction graph of journal entries over 10-day window. Maybe there were 100 journal entries over 10-day window. We union all of those graphs. So each journal entry is a separate graph, individual graph. But if you union them, you get something like this. So again, it's directed, weighted, dollar amount not shown here, but weighted, node labeled, account type. But the other more interesting and hard thing for us was multiplicity, edge multiplicity. So there could be multiple things being purchased, right? If you bought 10 printers, well, all of them are separate, or you bought 10 different items with different dollars, these are all multiple edges between the same two accounts. So multi-edged graph. You see how many, there are more edges because in a company, typically we work with three different companies, there will be up to 300 unique accounts. So the number of unique accounts a company has is not big, no matter how big the company is. But the edges, multiplicity of edges is enormous. Okay, so then let's formalize the problem. Now I'm given a database of journal entries translate to node edge attributed multi-graphs with auxiliary information. So on top of the journal entries that you show, we also have meta information, we call it metadata, of the form who requested this transaction, who approved this transaction within the company, what was the effective date, what was the entry date, these like meta graph level or journal level information, right? The goal is to find these anomalous graph metadata pairs, instances that are unusual. So again, every journal entry is a graph. Every graph also has some metadata. Think of this as this like tabular vector. I have many of them over the maybe annual transactions of a company. The way we work with PwC is they gave us, here is all the journal entries of this company from last year. Find me anomalies, right? Like that. So there'll be millions of such transactions over the year. Each journal entry is, I'll show you the size statistics later. Small graphs, but a lot of edges. Okay. So there are two modalities here. Maria did a great job introducing multimodal data in the morning, and she also talked about crash course to graph neural networks, so I don't have to do any of that, thank you. But we have similar multimodal data just like they had. So multimodal, the first modality is graph, yes. So accounts as nodes, debit-credit relations as weighted-directed edges. Account type is the node label, like equity and liability and savings, etc. So this is a complex graph, if you will. Then we have metadata. Think of it as this second modality, a vector of attributes, like tabular data, of who is the approver, entry date, effective date, etc. Two modalities. So how can we make use of them to detect anomalies? Now you may say, okay, this is only applicable to accounting. No, there are other applications. In fact, we applied the same algorithm to human mobility. So what is a graph in human mobility? Human mobility means we're tracking humans with GPS trajectories, like we have trajectory information every day over many months. Well, this is simulated data we have, right? But you can imagine. So there we create daily graphs of activity from people. So we say every stay point, so we call every location, geolocation that a person spent 20 minutes or more a stay point. And then a stay point we label, it's a node labeled graph where is it home, is it office, is it a coffee shop, is it a restaurant, etc. And then if a person goes from home to the office, it's a trip, right? So we see them maybe driving or biking, and we'll put an edge. And we can annotate the edges, like how long was the trip, some aggregate statistics of the trip, the speed the person went, etc. So node labeled, directed edges, maybe multiplicities. If you've made multiple trips between home and office, you went back again after the kids went to bed, etc. Okay, and then metadata could be something like, who is this person? What timestamp is it of, right, etc. So does it make sense? There is an activity graph plus some metadata, similar modality. How do we find suspicious behavior? More examples can be given, maybe communication networks. So you can take daily email networks. Every node is an identity within a corporate. Maybe node label could be the title, manager, director, engineer. You can have email relations as directed edges, and then you may have length of the email or some embedding of the text of the email as the node edge labels, etc. And then metadata could be what division of the corporation it is, what timestamp is there, very similar. So two modalities. So applications can be extended. And if you look at the literature for detecting anomalies with such complex data, what we do not see is as follows. There exist algorithms for detecting node at edge or node or edge level anomalies, whereas now we have a graph database with multiple graphs, each graph being a journal entry or an activity graph. A lot of algorithms cannot handle directed multi-edges. Edge multiplicities are not handled well. And there exist some non-deep learning based approaches, and with such complex data today, it's hard to imagine not using neural networks these days, right? But there exist some compression-based motif counting and compression-based techniques, including of our own, but they don't scale whatsoever, right? You need approximation algorithms, and they don't scale very well. And also, they cannot handle jointly graphs and metadata. This fusion of modalities that you can do very effectively with attention or, right, Maria, you said concatenation or cross-attention, like those kinds of things, neural networks unlock immediately. So we will look at a neural network-based approach. So the input is this node edge attributed multigraph along with meta feature vector. And this is our framework. So I'm going to break this into 5 pieces. I number them here. 1, 2, third component, 3, 5, 4, 5. I'll zoom in. I don't want you to take in all at once, but what we will notice is, I don't know if you see these like shaded things. These are parameterized neural networks. Every one of them is. And input is this multimodal input, like the graph along with the meta features input, and then it goes, and at the end we have this loss function I'll introduce. But all these parameters of this model are learned end to end, right? All these parameters simultaneously at once, right? You said, I don't want to do this and then aggregate, and those days are over, right? So we want to like fuse everything and end to end train things. So that's what we're going to do here. Okay, so multi-edge representation learning is the first step because today's graph neural networks accept only one vector edge vector at a time, right? They don't handle edge multiplicities. So, but easy peasy, what we do is we will simply flatten all the edge multiplicities between 2 nodes with deep sets. So deep sets is this algorithm for like representation learning solution for set input, set of vectors. And it is universally, so it's a universal function approximator. So just like MLPs are for vector data. So all these edges between 2 nodes will be deep setted into a single representation. Okay, so we need these parameters to be estimated. Now basically it's a single edged graph, right? We compressed all the multi-edges between 2 nodes. Then we'll do graph level embedding while we feed this graph, node and edge labeled graph, into a GNN. We use GIN here because it's provably expressive. It's an expressive neural network, but you replace with your favorite graph neural network, right? It will give you node embeddings. Then we will pool them into a graph embedding, maybe mean pooling or other more sophisticated poolings you can have. We will have a graph level embedding. Now, I flattened the graph into a vector. Now I'm in like structured data mode. And now I also had the meta features, remember, as the second modality, which is also a vector. Well, let me project each one of them or learn to project. These are parameter vectors, right? And then concatenate, that's how I'm going to fuse. And then toss the concatenated thing into another 2-layer MLP to come up with this final joint embedding, right? So this is the fused embedding. That's the next step. And final step, this final joint embedding goes into what we call membership estimation network, MAN. So it gives you a k-dimensional vector output, which is essentially a cluster membership estimator, right? So I'm going to actually, let me backstep a little bit. So what is an anomaly loss, right? When you train a neural network, for classification, well, cross-entropy loss, like you have loss, or autoencoder, you have reconstruction loss. What should we use as a loss for anomaly detection, right? Autoencoder can be used, right? Reconstruction makes sense. Or people have used one class learning, meaning learn me a center and put everything, map all the input to around this little center with small radius. So you're learning the normal pattern, right? Everything is compressed around a single radius. And your distance to the learned centroid is the anomaly score. So this is what people have done. We are kind of extending into multiple centroid because we believe, let's say with human mobility, there are multiple different people behaving differently. So we will learn K centroids. And the membership probabilities are estimated by this network. Given the final joint embedding, it translates it to memberships. So let's call for journal entry I, gamma IK is the membership probability, which is predicted, okay? And then the loss itself is this weighted distance of all the points to K centroids. So I is indexing points or journal entries or graphs. K is indexing the centroids. And this is the weighted squared distance to the centroids, which I'm trying to minimize, right? Again, I'm trying to learn tight centroids. This is the first term of the loss. Second one is entropy regularization. Of course, I want memberships to be like low entropy, so certainty assignments are more certain than not, so entropy is low. And the third term is I want the centroids to be as far as possible from each other, so I capture the diversity. I don't want them to collapse to the same, like mode collapse. To avoid that, we also add this determinant of the covariance matrix of the cluster centroids that promotes separation between the learned centroids. So this is my total loss, and through this loss, which is differentiable, right, you can estimate all of the parameters of this framework that I showed, deep set parameters, the GNN parameters, the projectors, the MLP, and the membership estimation network. All of those are estimated end to end through this loss. And the anomaly score is then the weighted distance of a point to the centroids. Right? The farther, the more anomalous. And then how do I do model selection? Because for neural networks, the entire architecture is a hyperparameter. Well, we actually use the loss of the first term of the loss to select. We select the model with the smallest, tightest centroids that could be learned. We evaluate this on 3 data sets from accounting domain. So these are code words for 3 companies that PwC shared with us. They have annual journal entry data. So this company is the biggest, so they have 150K journal entries annual. Small graphs, like sometimes one node, because they're general ledger, like we don't need to see the sub-ledger. So sometimes we have lots of self-loops to the same general ledger account, up to 90 nodes. Like these are tiny graphs, but many edges due to multiplicities. Node attributes are a number of account types, and meta features are the ones that I mentioned. It changes from company to company, but usually approver, requester, etc. is all there. For human mobility, we have 140,000 individuals simulated on a city like LA, and then daily activity graphs are small because a person usually does one or, not too many activities. Home office, that's it, right? Maybe, right? So up to 22 different activities. Multi-edges, node attributes, type of POIs, like are you at home, office, restaurant, etc. 41 unique attributes. Edge attributes are there, like trip properties, like duration, speed, etc. Okay. So here, evaluation is through injections. So we're injecting graph anomalies and metadata anomalies. Graph anomalies, we do label swap. So that's mimicking maybe entry error, like you deposited to the wrong account or you visited an unusual POI. Path injection mimics money laundering. So we delete an edge, inject a path from U to V instead. Things like that. Metadata anomalies, we change the entry and effective date or who approved, like these kinds of injections we do. Yeah, big table, but we compare to many baselines where we show that we do really well. What are the baselines? The baselines will be things like, let me learn a graph level embedding and then throw it to an outlier detector, like 2-stage approaches. That's why you see this plus this. It's a graph representation plus an outlier detector. Or if you're doing outlier detection in both modalities, then you're aggregating them post hoc, things like that, like not unified framework, but separate. And those do significantly worse, where the stars represent the significance level. And model selection works well, so let me skip that in the interest of time. We do some ablations showing that deep set is advantageous, using metadata is advantageous, and then using a k-centroid loss is more advantageous than one class. In summary, here we showcased an anomaly detection approach for a database of complex graphs with metadata. It can handle complex graph data, but of virtually any time. If you don't have multiplicity, it's fine. If you don't have node features, that's also fine, right? Like graph neural networks can accept anything and everything. At this point, we're looking at the most generic setting. It is widely applicable to other domains. As I said, we applied this to mobility data, and it's a unified end-to-end trainable model. And it's accessible at this link. With all of that, I thank you for your attention.
So questions from the audience, please.
Thank you very much. Very nice talk. So my question is that actually we had some multimodal features which were fed into a different neural network than the GNN that was getting the graph as input, right? So we are treating these certain information, augmented information in different way, embed them using an NLP, and also embed the graphs by GNN into steps 2 and 3, I guess, right? So my question is that what happened if we, instead of just feeding them to a different neural network NLP, we add those features, which I believe, I think it's in the graph level, not node level.
Graph level, yeah, they're graph
so
level.
We can add them as augment them as a feature, new feature, to original one, to every node of the graph, right? So basically, you have some initial features of every node, and then add these additional features as a constant vector to every given node, right? And then remove this NLP part, right? And give everything to just GNN, right? Of course, it is a constant vector adding to every node, but it encodes still this information in a GNN base, right? So
I see two issues with it.
And it removes some part of this. I mean, it would be 4 steps instead of 5.
Yeah, I see two issues. One, you're replicating information, right? This is graph level. You're attaching the same information to every single node, so it's kind of redundant. But more importantly, I think, so graph neural networks do like neighbor convolutions. So they learn properties of a node through the other properties of there's usually homophily assumption. So it's not clear to me why a graph level property should be learned from the neighbors of a node. I guess it wouldn't learn anything per se, right? It's constant vector, so you're just, so there is no semantic to why we would want to do that. It's really graph level, and keeping it that way could later on help us maybe with interpretable better. There was a question earlier, because the anomaly is at the approver level. So as soon as you may convolve it in with the neighbors, and like you're adding layers of complexity, and it's not clear what that does to that information. Keeping it separate, it's easy. So if something stands out, the approver is unusual. Well, let it be there as a feature, blatantly observable and interpretable, I guess, right? With graph convolution, it adds a little bit of layer of complexity, but I have to think about it, like what it would do. Thanks for the suggestion.
Further questions?